Hello everyone. So let us introduce the perturbation theory in quantum mechanics, the time independent case. So let's try to understand what do we mean by time independent case. So basically your Hamiltonian is not a function of time. Okay, that's it. So if you have a Hamiltonian, it might look like this. Say for a two level system, it might look like this. So in this case, there is no time involved. Okay, and the equation might look like what? So given this is the Hamiltonian and you have these states, so what I am going to do is I am going to use a new terminology. I am going to introduce something called a zero, which tells you that this is the original Hamiltonian. Okay, and for this original Hamiltonian I have two eigenstates. So one will look like this and another is going to look like this. So don't get confused with the notation, these are very simple stuff. Okay, so now you have a Hamiltonian and these are the eigenstates. So what are the eigenvalues? Since it's a diagonal, the eigenvalues are lambda 1 is equals to E1 and lambda 2 is equals to E2. These are the eigenvalues. Okay, now what does it mean? It means that when I act H naught on this state, I get its energy back, which is E1, which is quite clear, and then when I act H naught on this state, I get its energy back, which is E2, and this information is already there in the Hamiltonian. Okay, this is simple enough. Now the idea is we are going to add perturbation to this original Hamiltonian. This is the original Hamiltonian. Just if you look at the last lecture where we dealt with the matrix case and we understood perturbation from the matrix point of view, this Hamiltonian is which describes the two level system is nothing but a matrix, and the idea is the same, that you introduce a new Hamiltonian which is equivalent to the old Hamiltonian plus some extra term which is very small in nature. So basically another interesting thing about perturbation is, so consider you have two different Hamiltonian and these Hamiltonian, they don't differ much, they differ by a very small term. In such a case, given we know the solution of this Hamiltonian, by solution we mean the eigenstates and eigenvalues, we can actually find the solutions, eigenstates and eigenvalues of this new Hamiltonian using this perturbation theory. That's the whole idea. So how do we add perturbation? As I said, so the old Hamiltonian is E1 0 0 0 E2, and I'm going to add a very small perturbation, some off diagonal term that contains this kind of epsilon that we did before. Now what is a new Hamiltonian? That implies the new Hamiltonian is going to look like this. So exactly kind of similar case that we did before in the matrix lecture that we did last. Now you would say that okay, it's quite interesting and it's quite simple, we can move on and we can find the eigen values which are nothing but the energies. So we can find the corrections to these energies, and let's do one more thing. Let us introduce 0 also in these energy terms. That tells you that this is the initial case. So let us introduce this 0 and the 0 here and the 0 here. Okay, so why are we doing this? Because then for this particular Hamiltonian, I expect that this E1, which will be the eigenstate of this particular Hamiltonian, will be nothing but the eigenstate of the old Hamiltonian. I mean, this is the eigenvalue, sorry, the eigenvalue of the old Hamiltonian or the energy values plus some extra term, and maybe this is the first order correction and this is the second order corrections. Okay, I am assuming that this is true. So last time when I worked with the matrix, I showed you that this is true, but now I'm going to use a different route and both the roots are same. So here what I do is I assume that this is true. I assume that my new Hamiltonian, the perturbed Hamiltonian, is such that the eigen values, which are these energy eigen values for the new perturbed Hamiltonian, is nothing but small changes added to it. Okay, and the first order and second order correction. So when I do the same, I can similarly I can say that okay, maybe the same is also true with the eigen states. Maybe the eigen states of this Hamiltonian, which is x1 state, maybe it is such that it is x1 0, which is the eigen state, and there will be some extra terms, maybe x1 1 plus second order term x1 2, and similarly we can write the same for x2, which is nothing but x2 0 plus some extra term. So these are the first order corrections, and then there are second order corrections. Okay, so now the idea is clear. The idea is that we had a Hamiltonian not perturbed, and then we add a little bit of perturbation. That means we change the Hamiltonian, and the change is such that there are some off diagonal terms, and these off diagonal terms are very small. That's the whole idea. Okay, and then what I'm expecting is, oh, so I used epsilon. Let's not use epsilon, because epsilon is the value in the matrix. So let's use lambda, because lambda is a value that keeps track of whether it's a first order correction or second order correction. So it's just the introduction of lambda is such that to keep track of which order we are dealing with. So now the idea is different. Instead of finding the eigenvalue and eigenstate of this matrix directly, which we did last time, we are going to follow a different route. The different route is that we assume that this is true. We assume that this is true, and then we plug it into the equation and then move forward. Okay, so it's a new way, but it is also going to lead you to the same answer if you directly find the eigenvalues and eigenstates. Okay, so let's do this. So now you have this new Hamiltonian H, which act on x1 and gives the energy E1 x1. Okay, and note that this is different from the actual Hamiltonian, which acts on x1 0, and it gives energy E1 0 and the state x1 0 back. And what is the relation between x1 and x1 0? x1 can be expressed as first x1 0 plus some extra term. Okay, that's the connection. And what we are planning to do is that we are going to use this equation and plug what we know. Okay, so what are the things we know? So I know that the state x1 is nothing but x1 0 plus lambda x1 1 plus lambda square x1 2. Okay, and then E1, the eigenstate, is nothing but E1 0 plus some lambda E1 1 plus some lambda square E1 2. And what we are going to do is we are going to plug it here. Okay, and then there will be some maths. So let's plug it. It's going to be a little bit big, but let's plug it in. So it will be like this. So what is your H? It is H naught plus some epsilon V. Did we introduce V? So I can write it as epsilon V, where V is 0 1 1 0. Okay, I can also introduce in this way, and epsilon is a very small value. So this is this term, and then what is the x1 state? It is x1 0 plus lambda x1 1 plus lambda square x1 2. So don't think of this as x1 square, makes no sense, just corrected values, and we plugged it here, and the other side we need to plug e1 0. We made a mistake. The mistake is, since these are eigenvalues, there is no state stuff here. Since these are eigenvalues, there is no state here. The state, the cat representation only is allowed when you are dealing with eigen states, not eigenvalues. So e1 0 plus lambda e1 1 plus lambda square e1 2, and then again you have x coming back. So again x1 0. So looks a bit big, but actually it is very simple. Lambda square x1 2. Okay, so now how to solve it? It's very simple. You multiply them, collect the terms, and I mean, when you collect the terms, it looks like this. So you have a term like h naught x1 0, and then if you collect all the lambda terms, then inside it you get h naught x1 1 plus v x1 0. Okay, and then if you collect all the lambda square terms, then what do you get? You get v x1 1 plus h naught x1 2, and so on. Similarly, you do the same thing here. So you get this e1 0 x1 0 here, but then you have this lambda, and let's collect the terms here. So what do you get? You get e1 0 x1 1 plus e1 1 x1 0, and again the lambda square terms. So I'm just trying to give you the result, and you can just solve it yourself. It's very simple. e1 0 x1 2 plus e1 1 x1 1 plus e1 2 x1 0. Okay, now what you do is you collect the terms. For example, if you collect all the first order terms, all the terms that had only lambda, and if you equate that, so what do you have at hand? You have h naught x1 1 plus v x1 0 is equals to e1 0 x1 1 plus e1 1 x1 0. It's very simple algebraic kind of stuff. And then what we do cleverly is we multiply x1 naught bra vector both sides. Then you have this term, so I'm going to write it, and then you have x1 0 v x1 0, and then you have this term here. Oh, this is equals, you have x1 0 e1 0 x1 1 plus x1 0 e1 1 x1 0. Okay, now it's quite simple. The Hamiltonian, since it's Hermitian by nature, it acts on this. When it acts on this, you get e1 0, and this term becomes similar, and then we can cancel it off. Any standard book will tell you how this is done, and then in the end you are left with uh, x1 naught x1 naught, and this e1 1 goes outside, and the other side you have x1 naught v x1 naught. So again this becomes 1. So what is the first order correction in the eigenstate or the eigenenergy? It looks like this: x10 v x10. So this is the most general term that we can calculate for this two level system. Now the idea is the following: let's look at our Hamiltonian, how it looks, and let's actually calculate the first order correction to energy. So if you do this, then what is your x1 naught? It's 10. And what is your v? So v is 0 epsilon 0, and then this is 10. Okay, but you know that I think we made a quite a mistake. So we introduced v with epsilon separately, but I think we should not have done that. Let me check. So yeah, we made a mistake. I think we made a mistake here. When we introduced this epsilon here, we actually forgot to include epsilon in all this. Okay, so this will come. So instead of or you can think of it this way: instead of epsilon v, so you just include epsilon in all the v's. So wherever you see v, just put an epsilon. Let's see if there is any other v. No. So wherever you have v, put this epsilon, and now this is correct. But quite interestingly, you see that the first order correction is actually 0. Now you would say that, okay, does it mean that even after adding perturbation there is no change in the eigenstate, which makes no sense? No, this is not true. Even though this term becomes 0 for our specific case, but we are yet to see what this term gives, and you will see that this particular second order correction turns out to be non-zero. So let me just write the formula for second order correction, uh, which can be written not only for two state but for many state. So in that case you have the second order corrections to energy summation m not equals to n, and when we are using m and n, I mean that we can have states that are large, that it's not a two level system anymore, it can be many level system. So this is the most general formula. So xm0 v xn0 square divided by en0 minus em0. Now this is very simple to evaluate. So basically, since we have only two states and this m is not equals to n, so there will be only one term. So let's see what E12 is. So E12 simply becomes x20. I think we should have epsilon v, okay, and then it is x10 mod square divided by E10 minus E20, and then when you do this calculation you actually get epsilon square divided by E10 minus E20. Okay, so let's see if we are correct. So in the first case we got x10 and x10, but in the second case we got x20 and x10. So just do the calculation and see if I am correct. So what happened here? So what we understood is that the actual eigenstate is actually the eigenstate of the unperturbed state, and then this is the extra term that I was able to find out. So this was quite interesting in nature. It's because we did it in a different way, but you would reach to the same conclusion if you exactly follow the technique that I described in the previous lecture. That is, you take the Hamiltonian, which in this case was E10 epsilon e to 0. You take this Hamiltonian and find the eigenvalues and eigenstates of these Hamiltonian, and then you will see that one of the eigenvalue looks like this, and let me write another eigenvalue. Let me just write the result, which looks like this. So E2 is nothing but E20, which is the eigenstate of the unperturbed state, minus epsilon square E10 minus E20. Quite interesting, right? And then you can also find what happens to the eigenstates. So let me just write it here. And quite interestingly, you see that the new eigenstate, they look like this. They look like 1 and this epsilon divided by E10 minus E20. Now you would say, how does it look? It looks like 10 plus 0 epsilon E10 minus E20. So this is the correction term. So basically this is nothing but the x10 plus some additional term. So basically you see that the eigenstate, they also gets perturbed, and you get new eigenstates which are nothing but old eigenstate plus some very small perturbation perturbed state. Now in this case, when epsilon tends to 0, you get back your original eigenstate and eigenvalues, which is very easy to check. If your epsilon tends to 0, then this term goes to 0, this term goes to 0, your Hamiltonian, these terms goes to 0, and you get back your old solution. So this is the time independent time independent perturbation theory in quantum mechanics. Also there are formulas to find the eigenstate cases. For example, one formula for finding the first order correction to eigenstate may look like this. So summation m not equals to n xm0, then we have epsilon v, you have xn0, and then there is a state xm0 and divided by en0 minus em0. So it's very easy to do the calculation and find out that this is actually this. So what we learned is that we can do the perturbation theory in quantum mechanics, at least in the two level case that we showed here, either in the matrix style that we talked earlier. If you do this, you get the same result, or you can, instead of saying that okay, let me do the eigenvalue and eigenstate calculation directly, instead of doing that, what you can do is you assume that okay, there is a perturbation and the term should look like this. You assume this, and then you move forward. So this is another way to do this. You can do this technique also in this matrix case. So instead of actually finding the eigenvalue and eigenstate, you can actually assume that this is true and then move forward with the calculation, you get the same result. So in the next lecture we'll talk about time dependent case. Okay, that is quite little bit non-trivial in nature. It's not as simple as the time independent case, but we'll look at it in the next lecture.